For those of you at home, you should have your classification notes ready. All right. We are still living in a world of review, of course. Um, Today is going to be, we're going to start off with vocab that's super low level foundational stuff that I just need to remind you of, but it leads in to a skill that we didn't do last year. All right. The analysis of particulate diagrams. Yeah. Okay. So make sure you're on your toes because you do have a brand new skill that I need you to get good at. Now, remember for general note, I'm not writing anything on the whiteboard during this lecture, but general note taking skills, I would have your utensil up. I'll give little examples here and there. So keep filling in your margins with good stuff as we work through this. Okay, let's start simple. The phases of matter are solid, liquid, gas. We don't have to talk real deeply about what that means in terms of particles. Like, you already know. If I said, hey, there's a sample that's got particles that are really far apart, which phase of matter is that probably? Yes, right? Because the solids are the ones that have the particles way closer together. Solids tend to have much more organized setups where the gases are more random and everywhere. But we don't go real deep into it now because in second semester, there's a unit called solids and liquids, and then there's another unit called gases, gas laws. So we're gonna get into the deep stuff later. Matter is what's studied in chemistry. If you remember from last year, it's anything that has mass and volume is what we study in this class. Of course, lots of different angles of it. But in regard to classifying it, we start off real simple with pure versus mixture. A pure substance is one that is already as simplified as it can be. You can't take a pure substance, work with it on your desk, and break it down into something smaller. And it comes in two forms: elements and compounds. So, elements, boom, all those squares up there. If it's got its own square on the table, it's an element. And they're pure. I can't give you a piece of magnesium and say, hey, break that down into its parts physically. You can't do it. Magnesium is in its simplest form. But so are compounds. What's a compound? By definition, a compound is two or more different elements that are, well, bonded together. But even those are pure. Like if I give you a couple H's and an O, water, to mess with at your desk, you can't physically break the water down into smaller pieces. Chemically, you could do some stuff, but that's not what this is talking about. Physically, both elements and compounds are as simple as they can be. But if you're dealing with a sample that can be broken down or separated into subsections, those are your mixtures. And mixtures, as you probably remember, come as both homogeneous or heterogeneous, and that's a big part of today that we'll need to recall. The prefix homo means same. A homogeneous mixture is one that is the same throughout. Essentially, when you're building a homogeneous mixture and you're mixing stuff together, the parts tend to disappear when they become mixed together. The initial example I used last year for homogeneous was Kool-Aid, right? Oh yeah, juice. Because to make Kool-Aid, you have your water, your sugar, and your powder. But once you mix them together, it's gone, right? You can't see those individual parts because it becomes this uniform mixture. To the point where it dissolves so evenly that if you make Kool-Aid correctly, if I give each of you a sip of made Kool-Aid, it should all taste the same for everybody. But that's not how a heterogeneous would work, because a heterogeneous mixture, everyone would have a slightly different experience, because it's not evenly mixed. What's a good example of a heterogeneous mixture? Trail mix. All three classes went to trail mix for that question. I'm glad that that's our shared example. Yeah, but trail mix is a good example because if everybody took a handful out of a trail mix bag, you'd all have different amounts of different stuff, right? It's also very easy to see those components. Delicious tech Chex pieces, little wafer things, ruin your day pretzels. You can identify all of the parts very simply, way easier than you can a homogeneous mixture because that's where they're harder to see. We'll be applying all of this vocab to our particulate diagrams here in just a moment. But first, we'll end with changes. Chemical versus physical changes tends to be something you're good at. It's when our sample of matter undergoes a change, something happens. But if it's physical, nothing new is formed. If it's chemical, something new is formed. The example I give in class a lot is the paper. All right, we've got a pair of the paper is physical. It is a change. I did something, but you can't find anything new in my paper tear, right? It's not like, oh, there's two pieces now. No, there's, okay, but there's nothing new. I have the exact same amount of paper. But if you introduce other types of changes, something a little different, so that it's more than just me talking. But if we introduce another kind of change, we will have a new something formed. What's new here? Ash. Yeah, we didn't have ash before. So another type of change, but with a clearly brand new substance. Let's practice for a second. Photosynthesis. Is photosynthesis physical or chemical? It is chemical, because in photosynthesis, you start with carbon dioxide and sunlight. What do you end with? Glucose, sugar, and oxygen, brand new stuff. It's kind of like ice melting. Physical. It's important to think about phase changes. Y'all are sometimes really bad at that. All right, if these items are changing between each other for a sample, that is a physical change, not a chemical. All right, some of y'all are like, oh, but I had ice and now I have water, something new. It's not new. It was always water. Canvas is going to give you practice on this. All right, practice on this review, and it should hopefully be easy practice, but you'll get some repetition. It's going to give you practice on this as well. I'm not going to teach you this again. Actually, your ability to count subatomic particles, protons, neutrons, electrons, is not something that will be directly tested on the AP exam, but it is a good foundation that a lot of other things rest on. So, again, Canvas will give you some practice on it. If you are lost, then, come see me. But you've done this, and it's very low-level thinking for the most part. Real quick, though, how many of y'all saw the links I posted Friday afternoon? Should be everybody, because you have push notifications on. Yeah, I sent out an announcement on Canvas that had links to honors lectures that directly correlate to this roadmap only. So if during the rest of this unit you run into the issue where I don't know how to find how many protons there are in titanium, one of the videos I linked goes over how to do that. So anyway, they're there. They're not required watching, but some of this on your own stuff, you might get some help there. What we need to practice doing, though, is particulates. Now, this screen was a late add. I mean, it's been there for several days, but when I started flipping through my notes, I left myself a note last year to add this. So, what this is it's the rules of what we're about to do. You do not need to speed copy it right now, because I'm about to take it off, but I just want you to realize that in a moment when I'm talking about things being disconnected or shapes being the same or different, you're like, wait, I need to write that down. No, you don't, because you have access to this now. You're probably going to catch on without writing it down anyway. because this isn't hard what we're about to do, but this is there. The words I'm about to use are supported by this slide that you now have access to. All right. Particulate diagrams are visual representations of samples of matter, but they're drawn in such a way that you can apply states of matter and classification, meaning that based on the way these are drawn, I know whether they're solid, liquid, gas, and I know whether they're element, compound, mixture. And if they're mixture, I also know whether they're homogeneous or heterogeneous. So it's a ton of information from these little doodles that you might be asked to analyze. We'll start slow, but you'll catch on pretty quickly. So here we go. Let's start with A. Let's start with states of matter. If they want you to think solid, then the symbols are going to be organized along the bottom of the square. Again, you don't paraphrase me on this. You're going to catch on to this. These subtleties are very easy. If it's a liquid, the shapes are going to be disheveled slightly along the bottom of the square, showing you that it's not floating around, but it's not as organized as it could be. Gases will be floating around the square. So look at A. What state of matter do you see?
Gas.
Definitely a gas. But what about element, compound, mixture? All right, well, let's do it again. If there's only one shape in the particulate, only one type of shape, it's an element. If there's two types of shape, all right, and they could be different sizes or different colors or literally different shapes, but if there's two clearly different types that are touching each other with consent, then it's a compound. If you have two different shapes that are not touching each other, it's a mixture. So let's go through that. Let's apply that. Look here. How many different types of shapes do you see?
One.
Just one. So what is A? Element. So it's a gaseous element, and we're done with A. A is a gaseous element floating around the square and only one type of shape. What states of matter do you see in B? There's gas floating around up here. What else? And liquid, because we've got stuff along the bottom, but they're not organized along the bottom. Are there different shapes in the particulate? There's a lot of different shapes. I've got big circles, little circles, and dark circles. Are all of those shapes connected? No. The moment you have disconnected different shapes, it's a mixture. But mixtures are either homogeneous or heterogeneous, so we can keep going on this. Which one's easier to separate, homogeneous or heterogeneous? Heterogeneous is easier to separate if you think about Chex Mix versus salt water or sugar water, whatever, Kool-Aid. If the particulate is drawn in such a way that you could use a singular line to separate and group the different items, then it's heterogeneous because it's being easy to separate. It doesn't even have to be a straight line. It can be a slightly curved line, as you'll see soon. But this example is a heterogeneous mixture, gaseous and liquid components. I know it's heterogeneous because I could just draw a line right there and it would separate it into subsections. Look at C, gas, liquid, or solid?
Yeah.
Gas. They're floating around the square. All the same shape or different shapes? Different, because remember, size is something. We've got small and big circles. Touching or not touching. So it's a mixture. If they're disconnected, it's a mixture. So it's a gaseous mixture. Homogeneous or heterogeneous? This one's homogeneous because look, there's no singular line that I can place that will easily separate them. Homogeneous gaseous mixture. What state of matter is D? Liquid, disorganized along the bottom. Element, compound, or mixture? Compound. Different shapes, dark and light, but they're touching. Automatically a compound. All right. Solid, liquid, or gas for E? Solid. Very organized along the bottom. Very predictable pattern. Element, compound, or mixture? Compound. Different size shapes, big and little circles, but they're connected. So it's a solid compound. Anybody know what the common name of E is? That's not what the common name is. What's the common name? Starts with an I. Ice. Yeah, it's ice. That's solid water. That little Mickey Mouse shapes, the oxygen with its two hydrogens. You don't have to know that, but it's ice. What about F? We can go a little bit quicker now. What do you think F is? Solid element. Only one type of shape, organized along the bottom. Solid element. G is a wild one, though. G comes with a gold star moment. Who wants to impress Cummings today? There's a vocab word that describes, outside of what we've been talking about, that is a good description of what G probably is. Anybody? Starts with a D. I mean, there's a version of that that's not a terrible guess. But what's Brinkelhoff? Anybody remember what Brinkelhoff? So the diatomic elements are 7 elements that can't exist alone, and they bond to a copy of themselves. Look what's happening here. Do you see how there's only one type of shape? There's only one type of shape, so it's an element. But do you see how they're bonded to brothers of themselves for some reason? All right, so this is a gaseous element. The answer is gaseous element. But I can tell it's diatomic because for some reason the elements are bonding to copies of themselves. You're not accountable for that right now. We'll recover diatomics later. But y'all are actually the first AP class today that no one came up with before me. Uh-oh. What's the answer to H? Gaseous element. H is a gaseous element. Is this all right? Sweet, because I'm going to give you 2 minutes to do the next page of them, and then I'm going to draw cards and call you out. Go ahead and take a couple minutes and do the exact same thing before I draw cards. If you want to talk to someone sitting near you, that's fine with me. Yeah. No. Cut that out. No, I don't edit. What's that? Oh. What? Oh, okay. So how to move. Maybe 4 minutes. Don't be nervous.
What are we doing? You say hi. You say hi. You can't see it. I'm getting it back later.
He's there. How did we do? If I call on you, or rather, if the deck calls on you, because I'm a nice person that would never dare call on you. I'll walk you through it. Just go solid, liquid, gas, and then element, compound, or mixture. And if you freeze up, we'll have a conversation. We'll get there together. All right, so let's start with I. Here we go. Let's head over to cluster 1. Seat 4. Hey, 1-4. What did you get for I? Liquid element. Agree or disagree? Liquid element's perfect. Stop me if you need to. J. Let's go to cluster 1. Seat 1. What'd you get for J? 1-1. Let's go through it here. Let's start with solid, liquid, or gas. Not a solid because they're not organized along the bottom. Gas because they're floating around. All right. So then we go element, compound, or mixture. All right. We've got different sizes not touching each other. So not compound. So there is compound. That's a compound. So if you have different shapes that are connected, they're bonded, that is a compound. But the moment we've got different shapes that are disconnected, automatically a mixture. What type of mixture? Anybody? Heterogeneous, yeah. Because you could draw a line right there. Easily separated, heterogeneous. Let's go to K. go to cluster 2. Seat 6, Aspen. Oh, look, you get a chance to keep having fun. You can pass the bird now, though. All right, Aspen. So try this one, though. You totally go again. Because the first time it picked you and the second time it picked that empty desk. And so it activated Aspen. And now it's a good Monday, isn't it? Solid, liquid, gas. What do you think? Gas, because they're floating around. All right. Element, compound, or mixture. All right. So the element will only have a singular shape. Element, if there's only one shape in the square, all dark shapes. Help her out. What's the classification? Mixture. Different shapes not touching each other. Homogeneous or heterogeneous? This one's homogeneous because, again, no singular line could be drawn to easily separate. Let's head over to L. Cluster 1. If it does you 3 times in a row. Seat 6, 1, 6. What did you get? Liquid's a good guess. I think liquid for sure. Some of y'all will be like, well, they're kind of floating up. But if it was gaseous, I feel like they would have been more dramatic with the float. So I feel like it's a liquid that might be on the verge of evaporating, maybe. So liquid's good. What else? Yep, mixture. We've got different shapes that are disconnected. What type of mixture? Hetero is perfect. You could draw a little rainbow line, and it would be easily separated. Let's head down to M. Let's go to cluster 5. Seat 1. Aspen, what did you get for M? Solid element. Do y'all like that? Yep, it's easy. Very good. Let's head over to N and go over to cluster 5. I'm going to keep trying to get you. Cluster 5, seat 4. Aspen, what did you get for N? Gaseous mixture, that's correct. Homo or hetero? Okay. Homo's correct. Homogeneous, not easily separated. How are we doing? Not getting a lot of questions. O is kind of fun. Anybody, what states of matter do you see in O? Solid and gas. It actually looks like it's a solid that is like turning into a gas kind of randomly. There's a fun, another little gold star opportunity here for what this process is called. We did learn it last year.
Oh,
Starts with an S. That's it. No.
sublimation.
Sublimation. Yeah, sublimation, again, you're not held accountable for that right now, but sublimation is a solid turning into a gas without getting wet. It's what dry ice does. But anyway, compound. This is compound. Different shapes, but they're in contact with one another. What about P? What'd y'all put for P? Anybody? It's a solid mixture. Organized along the bottom, mixture because those are not touching each other. Homogeneous or heterogeneous? Homogeneous, a single line is not going to separate those easily at all. It's actually an alloy. You don't have to know that yet. I will study alloys next semester, but an alloy is a a homogeneous solid mixture. Yeah. Oh, sorry. I thought you were raising. No other questions? All right. We're going to end with something that, excuse me, is not a lot of fun to talk about, but I have to talk about it. It's easy. It's just boring. Mixtures can be separated. We've been saying that all period. But College Board wants you to held accountable for 5 specific processes of separating them. This question usually comes in the form of an MCQ on the AP exam where they'll give you a situation and ask you which of the following ways would be the best way to separate this mixture. Your understanding of what they are is important, but I think it's most important for you to understand whether they can apply to heterogeneous or homogeneous situations. So I would take note of that while I summarize these real quick. Okay, the worst way to separate two things is decantation. Decantation is where you have a mixture and you literally try to carefully pour one part off of the other. An example of decantation, by the way, it's only for heterogeneous because you have to be able to see the parts that you're trying to carefully pour. But an example is like Italian dressing. If you went home right now and took Italian salad dressing out of your fridge, what's true about the way it looks before you do anything to it? It's super separated into like all the flavoring and then a layer of oil. So you could do decantation to try to separate that by undoing the lid and carefully pouring the oil layer away from the crispy layer. The problem, though, is that you would have flakes of the flavor in that oil that you pour off, and you would definitely have residue of the oil still in the flaky part because this is not a good separation technique. An upgraded version of this with your Italian dressing is filtration, which is something you're familiar with, especially if you're a coffee person. But filtration is where you take that mixture and you dump it through an intermediate that will let some things pass and other things not. Like, let's say I gave you a sample of sandy water, all right? And I wanted you to separate the sand from the water. Well, filtration would be a good way to do this because if you had a filter that allows water to pass but not those larger sandy particles, then when you do the pour, the water would go through and the sand wouldn't. And boom, you have filtered the mixture. Also only good for heterogeneous though. Now, we can take our first step towards homogeneous with our next example of separation technique, and it's one you're very familiar with, just evaporation, right? So if we have, this uses salt water, but if we had our Kool-Aid from earlier, all right, we said it's homogeneous, and I wanted you to unmake it. How would you unmake Kool-Aid? This process, evaporation, you'd boil it. And what would happen is you would lose all of that solvent, right, the water that created the Kool-Aid, and you'd be left with sugar, right? You'd be left with the flavoring also. You'd have to go through another process to separate that, but we could do it. But evaporation is a good way to basically add heat to a solution to remove solvent from a dissolved solute. The problem with evaporation is that you lose a component of the mixture. Like if we went back there and just boiled the water to get that sugar by itself, it would work, but the water component would be gone. So if there was any secondary analysis you were wanting to do with whatever mixture you were separating, evaporation has the drawback of losing a part of your mixture. So the much better version is distillation. Distillation can also be used for both hetero and homogeneous mixtures. But if you look at this setup, it doesn't force half of your mixture to vanish. If this is your starting mixture here during distillation, and you add the heat, well, you're going to cause evaporation, but you have a secondary setup that is made to trap the item that is evaporating and recondense in a separate container. So when it's all said and done, you still have everything. And you can do follow-up analyses on both the solute and the solvent that you have separated. Distillation is how they make beer. It's how they make gasoline. All right, gasoline starts as crude oil, and they go through a distillation process to separate components to create the gas. A big component of this working, though, is IMFs, which you are not held accountable for during this unit, but just because it's fun to ask, what does IMF stand for? Ooh, intermolecular force. Y'all remember that near the end of last year? That's fun stuff. We're going to study that again. I like to put it on the slide now, though, so that when we get there and then you go back and you're reviewing stuff, all of these things start meeting and talking to each other. Finally, chromatography. This is the only one that is used for homogeneous only. So that's an important thing. We're going to do chromatography not in this upcoming lab, but in the lab in Unit 2 as part of a series of experiments. But basically what you do is you take a homogeneous mixture and you put it onto a mobile phase, which is usually a special paper, and then you allow water to travel through that that paper and pull apart the mixture that you've already added, and you're able to see the mixture components that were usually invisible to the eye before you. Any questions? Cool, man. Hey, make sure you're taking advantage of links I post if you need to. We don't have lecture tomorrow. We'll continue on Wednesday. I also want to remind you at the very end of Friday, I mentioned scientific notation. If you don't remember how that works, again, one of the links, you could scrub and find the part that's applicable to you. But be responsible. Make the sound he makes when he goes fast. Do it. Make the sound.
Here's a mark. Here's a mark.
Oh, thank you.